To get to our modern astronomy, our modern understanding of the universe, we need to build up our scientific principles and to get to all these wonderful, phenomenal conclusions, such as like all the stars. All a star does is take light elements, fuse them together into heavier stuff. And we know by studying the stars that they will die, and when they die, they eject their material out. I like to describe it as a burping of material. The star doesn't have enough fuel anymore to fuse, so eventually it starts just burping all the material out. Or in this case, you could have supernovas, which are just giant explosions. And that ejects all of these heavy elements out into the cosmos. Well, those heavy elements out there, they'll start to coalesce, gravity will take over, and eventually new stars and new planets will form from these heavier materials. And it is not hyperbole to say that every atom in your body is once part of a star. We are literally stardust. All the atoms in our body heavier than hydrogen was fused in the core of a star at some point in the universe's history. And we need scientific principles and methods to learn this. Astronomy would be described as a observational science. We can't actually travel to the stars and take samples on the surface. We need to observe and use our physical models and equations to understand them and predict what will happen. And we need to scan the horizons. So, what exploration we can do of the universe, we're going to use technologies like lunar landers, humans on moons, hopefully in the near future, humans on Mars. But to get to understanding the bigger size of the cosmos, we need telescopes, satellites, rockets to send those satellites into space. So astronomy is this huge cross-disciplinary field. You got to have computer scientists, you got to have rocket engineers, you got to have biologists. If you want to try and answer the question of is there life outside of planet Earth, well, you need to know what the chemical signatures of life are. So you need to consult with biologists and say, well, what are the parameters? What can sustain a living organism out there? So with all that in mind, let's build up our scientific principles. What are the core concepts in science? Breaking down science into 3 components that are the easiest to digest right now, we'll say science is composed of our hypotheses, our principles, and our scientific theories. So a hypothesis has to be an idea. You're trying to answer a question with a hypothesis. And your idea, your hypothesis, has to be both testable and falsifiable. And it has to make predictions. You need all 3 components. Here is a classic example of an idea that is not a hypothesis. I claim there is a teacup orbiting Mars. Well, this is testable. Get your telescopes out, send rockets out in space and orbit Mars, and you can search for the teacup. This is definitely a testable idea. But prove me wrong, right? You say, hey, Mr. Neerum, I looked for months, I looked for years, and I never once found a teacup in orbit around Mars. And I'll just cross my arms and say, well, you didn't look hard enough. You just didn't find it. Well, then people send more rockets, more objects out there, and they still say, hey, we haven't found your teacup. And I'll say, hey, it's an invisible teacup, or you didn't look hard enough. So while this idea, in essence, is testable, it lacks the ability to be falsified. You can't prove that there's not a teacup. And what about the predictions? You're going to guess that there is a green tea in that cup. It has no utility, right? So when we talk about hypothesis, it has to be testable, falsifiable, and make powerful predictions. So let's go to an example of an actual hypothesis, and we'll follow this one as it goes up the chain. And one hypothesis initially was that the speed of light is constant. Well, you can very easily falsify that. All you have to do is scan the universe and find something going faster than the speed of light. If that happens, physics is broken. We have to reinvent, re-understand, and where we are now. So far that hasn't happened, and we don't expect it will to. And this speed of light, this hypothesis that the speed of light is constant, it leads to things like the theory of relativity. If you like using GPS, say on your phone when you're commuting, you're traveling somewhere, those will not work without relativistic calculations, without adjusting for the time dilation caused by being in a different gravitational well. And all that is a direct consequence of this idea. Now, upgrading. We can talk about our principles. These are foundational assumptions about how the nature of the universe works. And these are going to be powerful tools for us. Some scientific principles will be things like energy conservation. Energy cannot be created or destroyed. Same thing for matter. You can't create or destroy matter. You can just shift where it is. Another principle that's going to keep coming up for us over and over again, so you're going to hear me talk about this many times throughout the semester, is the cosmological principle. And there's lots of different ways to describe this. And first, I'll just say this way, is that the laws of the universe are true everywhere. And I'll have more to say about that one later. Upgrading again, we're getting away from hypotheses and principles. We're going to talk about our scientific theories. Now, these are the detailed, these are the powerhouses in a scientific idea. What you're saying is that when you have a theory, it has been rigorously tested. It wasn't just one person who proposed the idea and did some tests. There have been dozens, if not hundreds or thousands of people who have tried to break the theory, put it to its logical limits. And our scientific theories are going to be powerful calculations. One example of this would be Newton's laws of motions. Newton was asked, why does the moon cause the tides? And we will talk about that later. But Newton was asked why the moon caused the tides, and he came up with his gravitational theory and his laws of motions. And with that, he was able to explain why the moon caused the tides, but he's able to do more than that. He could calculate the positions of stars and planets. He could construct buildings. He could say, what are the physical limits, the forces and strains on this thing before it breaks? So even though these laws were written hundreds of years ago, they are still with us today because of how powerful this scientific theory is. Other examples of scientific theories that have been beaten and put to the extremes, things like Darwin's theory of evolution. We know through the generations that life is going through these minor changes, and sometimes those are evolutionary benefits, and it allows that organism to thrive. And we have been able to use this tool to predict where to find missing links. Einstein's theory of relativity, I've already discussed that a little bit, about how you can't have satellites working without these relativistic calculations. Maxwell's equations, a very common joke is to say Maxwell said, let there be light. This is in essence how electricity works. Maxwell was one of the first people to really say that electricity and magnetism are the exact same thing. And without this, you wouldn't be able to construct a laser. You wouldn't be able to build the fluorescent lights or get power from your wall, and so on and so forth. Coming back to that cosmological principle, we can phrase this in a couple of ways. And a pessimistic attitude is to say that our view from Earth is not special or unique. We're just one point in the universe looking out. And because we assume that the laws are true everywhere in the universe, that there's nothing special about us. But I don't like this pessimistic attitude that there's nothing special about our point in space. From a physical, a scientific point, Sure. But what really matters, where the real power comes from, is that distant objects are going to be like us. We can look at other stars, we can look at gases, we can look at planets, other planets. And by studying those, we can learn about ourselves. So because matter and energy must obey the same physical laws everywhere, we can study the cosmos. Wonderful quote. This is from the Goddard Institute for Space Studies, is that many of the tools that we developed in studying climate change on Earth can be adapted and used to study other planets. And it's a cyclical feature. We studied Venus, learned about the carbon trapped in Venus's atmosphere, how Venus is becoming such a hot planet. It's not just the proximity, it's due to the atmospheric conditions on Venus. And we studied Venus and were able to better model our own atmospheres. And because we're able to better model our own atmospheres, we can better model what's happening on Venus. And so it's this cyclical, growing process. By studying the universe, we learn about ourselves. And that is the true power of the cosmological principle. Science is a methodology to learn about the nature. You start with an idea. You have an observation, you see something, and you try and understand it. And you formulate a hypothesis that you make predictions with, and you test it. And you go through this scientific method to process what can you learn from this idea. Let's go ahead and zoom in here. When it comes to making a scientific methodology, you're going to ask a question. And it's going to be based on your current knowledge. As always, to be a hypothesis, you have to see if it's falsifiable and make predictions. So you go and do your experiment, you collect your data. And once you have your data, then you step back and say, look, I had this idea. Does the data support it or refute it? Well, if it supports your idea, you celebrate. You've learned something. You better understand something. Now you can continue the process. You say, all right, now that I understand this process more, what can I do with that? And that will motivate new questions, new ideas. And so there's this propelling forward of concepts. Now coming back to, well, what if the data rejected your hypothesis? Well, simple. You reject your hypothesis. And you still have gained some knowledge. You started off with a question. You had an idea that you thought you had an explanation. When you rejected your hypothesis, it's not a failure. We're so commonly taught, we're trained to believe that it's an error, that you made something wrong. No, even mistakes are a chance to grow and learn something. You know that method didn't work. There was something flawed in your reasoning. So then you can go back again and say, well, what about my idea? What about my hypothesis was wrong? How can I correct that? How can I get to the true nature of the universe? So when you have a scientific idea, you are constantly growing, and you're either going to try and address new problems because you gain knowledge, or you're going back to old problems. We discovered something new. We have a better understanding of physics in the universe, and we need to go back and reevaluate ideas that we had once accepted. And this is the greatest power of science. Science has a vulnerability. You can go back and say, we got something wrong. There was something flawed here, and this is a power of it. A classic example of this idea of science failing and growing because of that failure was Einstein's cosmological constant. This is an example. We always like to think of Einstein as that this is the pop cultural icon of intelligence. Oh, Einstein figured it out. And here is an example where Einstein got something wrong. When Einstein said the speed of light is constant, he wasn't the first one to kind of have this notion, but he was the first person to formulate it into a theory. And a consequence of his theories were relativity, that the universe was changing in size. At the time, the universe could have been shrinking or growing. We weren't certain. And Einstein did not like this idea. Einstein's worldview was that the universe was static, always here, always has been, and always will be. That was Einstein's worldview. That was his philosophical view. And when people started using the equations that he derived and said, look, this is what the universe looks like ages ago, and this is what's going to look like now, Einstein rejected that. He did not like this idea. So he proposed a cosmological constant. And he did that to try and fix his equations. He said, hey, the universe must be constant because it's always existed. It's the universe. And he tried to force this cosmological constant into his equations, into his theories about the universe. And years down the road, he rejected it. As more and more data kept coming in, as more evidence, as more experiments came in, he just couldn't hold on to his worldview that the universe was static, never changing. And Einstein ultimately called it his greatest mistake. He said he was wrong to try and fix his equations, and that we could have learned so much more if he wasn't resisting the idea. And this is what I mean by science vulnerability is its strength. We can be wrong about an idea and still make advances, move forward. Another example of a scientific concept that ultimately failed. You ever heard of the luminous ether? What the heck is this? When you go to the beach and you see the water waves coming in, well, what is the wave? Well, it's the water. The water acts as a medium. The waves travel through that. When I'm talking to you right now, you're hearing me. What's happening is that the speakers on your computer, on your device, is generating an audio sound. It's vibrating air between us. So the air compresses, stretches out. That compression wave translates across the material, across the medium to your ear, and you process that information. So the old tagline, no one can hear you scream in space, right? What does that mean? When you go into space, there's no air, there's no water, there's nothing to vibrate. All sound is something vibrating, something wiggling around. And in space, there's nothing there, no vacuum. It's just a vacuum. So how are you supposed to transmit a wave across that space? And at the point in time, this would have been a little more than a century ago now, when we had this idea of the ether. It was proposed that the luminous ether was this material, this substance that permeated all of space, like an aura. And it was to try and explain how light moves. Because how does light, an electromagnetic wave, just like a sound wave or a water wave, how did that wave travel through nothingness? And so people over a century ago try to use the luminous ether to explain that. Well, there's just something there, we just haven't found it yet. And as the evidence came in, we had to chuck that old idea out, to the point that we don't teach it anymore. It's a dead idea. It was a scientific topic of exploration, but when the evidence came in and did not support it, we had to reject it and move on in science. Continuing this theme of science being self-correcting, it's updating our ideas as we learn things. Some of you might still be old enough to remember back in 2006 the huge controversy when Pluto was no longer a planet, which I'm going to say now, Pluto is definitely not a planet. And here's the explanation. Here's why Pluto is not a planet. As we looked out, as we saw more things, had a better understanding of what's going on further out into the solar system, we found these other objects that weren't quite planets themselves. Pluto has a moon. Pluto's moon, they are so close in mass that they don't really, it's not like the moon on Earth orbiting us. Pluto and Charon orbit each other. So in light of these new objects we found, we had to eventually just create this new category of materials, and we started calling them the dwarf planets. Another term for them, for those of you who are still bitter about Pluto not being a planet, sometimes we call these Plutoids. Pluto has its own category named after it. Starting to wrap things up, one thing we want to emphasize is that science is, in essence, a mathematical thing. When we're trying to study phenomena, we're trying to make predictable patterns. And math, that is the language of patterns. When we're trying to create all these cool, fascinating ideas, we need some underlying mathematics to drive an understanding, to continue going forward. A weird, crazy example of mathematics and the universe being strange is something called a coastline paradox. And this isn't exactly an astronomy topic, but it's something I just want to emphasize to just get you some motivation there. Ever heard of a fractal pattern? The more you zoom in on a fractal, the more complexities, the more repeating patterns you can find. Well, it turns out that coastlines are, in fact, fractals. If you try and measure, use a long meter stick, a long measuring tool, you'll measure, say, the circumference of the coastline. Well, you try and get more accurate. You use instead of, say, using a kilometer, you start using 10 meters. And you start measuring the circumference using 10 meter segments. And the coastline will get significantly longer. And then you try using a foot. Use a shorter distance, and the perimeter, the distance that you're measuring across this, will change. So it turns out that even beaches, coastlines, obey this mathematical fractal pattern, and it's truly bizarre and fascinating how that comes out. And this is what I mean by science and mathematics. Mathematics is the language of science because math is the language of the universe. There can be new ideas. The more we try and understand the universe, as we discover more things, we'll have to reassess, reevaluate our ideas. And it doesn't matter how long we thought we understood something, how tightly we've held on to a belief. All that matters is that nature is the dictator here. The more we understand about the universe, the more we better revise and not just hold on to an idea just because we like it. Nature decides what is true. And our job is to try and peer into that box and try and understand it. As a brief summary, because we've covered a lot today, the speed of light, that's our unit of measurement. We're going to use the light speed, that constant c equals 3 times 10 to the 8th meters per second. And we're going to use that to measure scales across the universe. We talked about a cosmic address of how we start on Earth, go to the solar system, Milky Way, local clusters, superclusters. The universe keeps getting bigger and bigger depending on the scale we look at it. A light year is that 9.5 times 10 to the 15th meters, and our nearest stellar neighbor is 4 light years away. We all live in a universe that is 13.7 billion years old. And how do we understand, where do we get these principles? We know because of the cosmological principle that the laws of the universe are true here, they're true everywhere. And that gives us the ability to study the universe, to learn about ourselves. All right, see you all next time.